Good evening, and thank you for joining me for another Boring Books for Bedtime. I hope tonight's selection provides all the boredom your busy brain needs to quiet down and let you get some sleep. Before we begin, I'd like to give a special shout out of thanks to some new members of our Patreon family: Joan, Case, Chloe, Charles, Alpha, Sam, Beth, and Carolyn. Thank you all so much for supporting this podcast. By becoming members of Patreon, you help us remain 100% listener supported and ad-free for everyone, and it's very much appreciated. If you're interested in supporting Boring Books for Bedtime and finding out more about the perks available to subscribers, including exclusive episodes and full books found nowhere else, you'll find a link to Patreon in the show description. You'll also find a link to buymeacoffee.com, where you can support us with a one-time tip, no subscription required. I hope you'll take a moment to check them out. Now, let's read and relax. Find a comfortable spot. Adjust your volume. Take a nice deep breath in. Let it out slowly. And off we go. Tonight, let's relax with more from a book that attempts to explain some fairly complex scientific theories. We're reading The ABC of Relativity by Bertrand Russell, author of The Principles of Mathematics, Proposed Roads to Freedom, and Why Men Fight. First published in 1925 by Harper and Brothers, New York and London. Let's pick up right where we left off, in the middle of Chapter 8, Einstein's Law of Gravitation. Let's begin. It is important to realize that geometry, as taught in schools since Greek times, ceases to exist as a separate science and becomes merged in physics. The two fundamental notions in elementary geometry were the straight line and the circle. What appears to you as a straight road, whose parts all exist now, may appear to another observer to be like the flight of a rocket, some kind of curve whose parts come into existence successively. The circle depends upon measurement of distances, since it consists of all the points at a given distance from its center. And measurement of distances, as we have seen, is a subjective affair, depending upon the way in which the observer is moving. The failure of the circle to have objective validity was demonstrated by the Michelson-Morley experiment, and is thus, in a sense, the starting point of the whole theory of relativity. Rigid bodies, which we need for measurement, are only rigid for certain observers. For others, they will be constantly changing all their dimensions. It is only our obstinately earth-bound imagination that makes us suppose a geometry separate from physics to be possible. That is why we do not trouble to give physical significance to our coordinates from the start. Formerly, the coordinates used in physics were supposed to be carefully measured distances. Now we realize that this care at the start is thrown away. It is at a later stage that care is required. Our coordinates now are hardly more than a systematic way of cataloging events, but mathematics provides, in the method of tensors, such an immensely powerful technique that we can use coordinates assigned in this apparently careless way just as effectively as if we had applied the whole apparatus of minutely accurate measurement in arriving at them. The advantage of being haphazard at the start is that we avoid making surreptitious physical assumptions, which we can heartily help making if we suppose that our coordinates have initially some particular physical significance. We assume that if two events are close together, but not necessarily otherwise, there is an interval between them which can be calculated from the differences between their coordinates by some such formula as we considered in the preceding chapter. That is to say, we take the squares and products of the differences of coordinates. We multiply them by suitable amounts, which in general will vary from place to place, and we add the results together. The sum obtained is the square of the interval. We do not assume in advance that we know the amounts by which the squares and products must be multiplied. This is going to be discovered by observing physical phenomena. We know, however, certain things. We know that the old Newtonian physics is very nearly accurate when our coordinates have been chosen in a certain way. We know that the special theory of relativity is still more nearly accurate for suitable coordinates. From such facts we can infer certain things about our new coordinates, which in a logical deduction appear as postulates of the new theory. As such postulates we take 1. That every body travels in a geodesic in space-time, except insofar as electromagnetic forces act upon it. 2. That a light ray travels so that the interval between two parts of it is 0. 3. That at a great distance from gravitating matter, we can transform our coordinates by mathematical manipulation, so that the interval shall be what it is in the special theory of relativity, and that this is approximately true wherever gravitation is not very powerful. Each of these postulates requires some explanation. We saw that a geodesic on a surface is the shortest line that can be drawn on the surface from one point to another. For example, on the Earth, the geodesics are great circles. When we come to space-time, the mathematics is the same, but the verbal explanations have to be rather different. In the general theory of relativity, it is only neighboring events that have a definite interval, independently of the route by which we travel from one to the other. The interval between distant events depends upon the route pursued and has to be calculated by dividing the route into a number of little bits and adding up the intervals for the various little bits. If the interval is space-like, a body cannot travel from one event to the other. Therefore, when we are considering the way bodies move, we are confined to time-like intervals. The interval between neighboring events, when it is time-like, will appear as the time between them for an observer who travels from the one event to the other, and so the whole interval between two events will be judged by a person who travels from one to the other to be what his clocks show to be the time that he has taken on the journey. For some routes this time will be longer, for others shorter. The more slowly the man travels, the longer he will think he has been on the journey. This must not be taken as a platitude. I am not saying that if you travel from London to Edinburgh, you will take longer if you travel more slowly. I am saying something much more odd. I am saying that if you leave London at 10 a.m. and arrive in Edinburgh at 6:30 p.m. Greenwich time, the more slowly you travel, the longer you will take if the time is judged by your watch. This is a very different statement. From the point of view of a person on the Earth, your journey takes 8.5 hours. But if you had been a ray of light traveling around the solar system, starting from London at 10 a.m., reflected from Jupiter to Saturn and so on, until at last you were reflected back to Edinburgh and arrived there at 6:30 p.m., you would judge that the journey had taken you exactly no time. And if you had gone by any circuitous route, which enabled you to arrive in time by traveling fast, the longer your route, the less time you would judge that you had taken. The diminution of time would be continual as your speed approached that of light. Now, I say that when a body travels, if it is left to itself, it chooses the route which makes the time between two stages of the journey as long as possible. If it had traveled from one event to another by any other route, the time as measured by its own clocks would have been shorter. This is a way of saying that bodies left to themselves do their journeys as slowly as they can. It is a sort of law of cosmic laziness. Its mathematical expression is that they travel in geodesics, in which the total interval between any two events on the journey is greater than by any alternative route. The fact that it is greater, not less, is due to the fact that the sort of interval we are considering is more analogous to time than to distance. For example, if a person could leave the earth and travel about for a time and then return, the time between his departure and return would be less by his clocks than by those on the earth. The earth, in its journey round the sun, chooses the route which makes the time of any bit of its course by its clocks, longer than the time as judged by clocks which move by a different route. This is what is meant by saying that bodies left to themselves move in geodesics in space-time. We assume that the body considered is not acted upon by electromagnetic forces. We are concerned at present with the law of gravitation, not with the effects of electromagnetism. These effects have been brought into the framework of the general theory of relativity by Weyl. But for the present, we will ignore his work. The planets, in any case, are not subject as wholes to appreciable electromagnetic forces. It is only gravitation that has to be considered in accounting for their motions, with which we are concerned in this chapter. Our second postulate, that a light ray travels so that the interval between two parts of it is zero, has the advantage that it does not have to be stated only for small distances. If each little bit of interval is zero, the sum of them all is zero, and so even distant parts of the same light ray have a zero interval. The course of a light ray is also a geodesic, according to the definition. Thus, we now have two empirical ways of discovering what are the geodesics in space-time, namely light rays and bodies moving freely. Among freely moving bodies are included all which are not subject to constraints or to electromagnetic forces. That is to say, the sun, stars, planets, and satellites, and also falling bodies on the earth, at least when they are falling in a vacuum. When you are standing on the earth, you are subject to electromagnetic forces. The electrons and protons in the neighborhood of your feet exert a repulsion on your feet, which is just enough to overcome the Earth's gravitation. This is what prevents you from falling through the earth, which, solid as it looks, is mostly empty space. The third postulate, which relates the general to the special theory, is very useful. It is not necessary for the application of the special theory to a limited region that there should be no gravitation in the region. It is enough if the intensity of gravitation is practically the same throughout the region. This enables us to apply the special theory within any small region. How small it will have to be depends upon the neighborhood. On the surface of the Earth, it would have to be small enough for the curvature of the Earth to be negligible. In the spaces between the planets, it need only be small enough for the attraction of the Sun and the planets to be sensibly constant throughout the region. In the spaces between the stars, it might be enormous, say half the distance from one star to the next, without introducing measurable inaccuracies. At a great distance from gravitating matter, we can so choose our coordinates as to obtain a Euclidean space. This is really only another way of saying that the special theory of relativity applies. In the neighborhood of matter, although we can make our space Euclidean in any small region, we cannot do so throughout any region within which gravitation varies sensibly. At least, if we do, we shall have to abandon the view that bodies move in geodesics. In the neighborhood of a piece of matter, there is, as it were, a hill in space-time. This hill grows steeper and steeper as it gets nearer the top, like the neck of a champagne bottle. It ends in a sheer precipice. Now, by the law of cosmic laziness which we mentioned earlier, a body coming into the neighborhood of the hill will not attempt to go straight over the top, but will go round. This is the essence of Einstein's view of gravitation. What a body does, it does because of the nature of space-time in its own neighborhood, not because of some mysterious force emanating from a distant body. An analogy will serve to make the point clear. Suppose that on a dark night, a number of men with lanterns were walking in various directions across a huge plain. And suppose that in one part of the plain there was a hill with a flaring beacon on the top. Our hill is to be such as we have described, growing steeper as it goes up and ending in a precipice. I shall suppose that there are villages dotted about the plain, and the men with lanterns are walking to and from these various villages. Paths have been made showing the easiest way from any one village to any other. These paths will all be more or less curved to avoid going too far up the hill. They will be more sharply curved when they pass near the top of the hill than when they keep some way off from it. Now suppose that you are observing all this as best you can from a place high up in a balloon, so that you cannot see the ground, but only the lanterns and the beacon. You will not know that there is a hill or that the beacon is at the top of it. You will see that people turn out of the straight course when they approach the beacon, and that the nearer they come, the more they turn aside. You will naturally attribute this to an effect of the beacon. You may think that it is very hot and people are afraid of getting burnt. But if you wait for daylight, you will see the hill, and you will find that the beacon merely marks the top of the hill and does not influence the people with lanterns in any way. Now, in this analogy, the beacon corresponds to the sun. the people with lanterns correspond to the planets and comets. The paths correspond to their orbits, and the coming of daylight corresponds to the coming of Einstein. Einstein says that the sun is at the top of a hill, only the hill is in space-time, not in space. I advise the reader not to try to picture this, because it is impossible. Each body at each moment adopts the easiest course open to it, but owing to the hill, the easiest course is not a straight line. Each little bit of matter is at the top of its own little hill, like the cock on his own dung heap. What we call a big bit of matter is a bit which is at the top of a big hill. The hill is what we know about. The bit of matter at the top is assumed for convenience. Perhaps there is really no need to assume it, and we could do with the hill alone, for we can never get to the top of anyone else's hill, any more than the pugnacious cock can fight the peculiarly irritating bird that he sees in the looking-glass. I have given only a qualitative description of Einstein's law of gravitation. To give its exact quantitative formulation is impossible without more mathematics than I am permitting myself. The most interesting point about it is that it makes the law no longer the result of action at a distance. The sun exerts no force on the planets whatever. Just as geometry has become physics, so, in a sense, physics has become geometry. The law of gravitation has become the geometrical law that every body pursues the easiest course from place to place, but this course is affected by the hills and valleys that are encountered on the road. Chapter 9. Proofs of Einstein's Law of Gravitation. The reasons for accepting Einstein's law of gravitation rather than Newton's are partly empirical, partly logical. We will begin with the former. Einstein's law of gravitation gives very nearly the same results as Newton's when applied to the calculation of the orbits of the planets and their satellites. If it did not, it could not be true, since the consequences deduced from Newton's law have been found to be almost exactly verified by observation. When in 1915 Einstein first published his new law, there was only one empirical fact to which he could point to show that his theory was better than Newton's. This was what is called the motion of the perihelion of Mercury. The planet Mercury, like the other planets, moves round the Sun in an ellipse, with the Sun in one of the foci. At some points of its orbit it is nearer to the Sun than at other points. The point where it is nearest to the Sun is called its perihelion. Now it was found by observation that from one occasion when Mercury is nearest to the Sun until the next, Mercury does not go exactly once round the Sun, but a little bit more. The discrepancy is very small. It amounts to an angle of 42 seconds in a century. That is to say, in each year, the planet has to move rather less than half a second of angle after it has finished a complete revolution from the last perihelion before it reaches the next perihelion. This very minute discrepancy from Newtonian theory had puzzled astronomers. There was a calculated effect due to perturbations caused by the other planets. But this small discrepancy was the residue after allowing for these perturbations. Einstein's theory accounted for this residue, as well as for its absence in the case of the other planets. In them it exists, but is too small to be observed. This was at first his only empirical advantage over Newton. His second success was more sensational. According to orthodox opinion, light in a vacuum ought always to travel in straight lines. Not being composed of material particles, it ought to be unaffected by gravitation. However, it was possible, without any serious breach with old ideas, to admit that in passing near the sun, light might be deflected out of the straight path, as much as if it were composed of material particles. Einstein, however, maintained as a deduction from his law of gravitation that light would be deflected twice as much as this. That is to say, if the light of a star passed very near the sun, Einstein maintained that the ray from the star would be turned through an angle of just under 1 3/4 seconds. His opponents were willing to concede half of this amount. Now it is not every day that a star almost in line with the sun can be seen. This is only possible during a total eclipse, and not always then, because there may be no bright stars in the right position. Eddington points out that from this point of view, the best day of the year is May 29th, because then there are a number of bright stars close to the sun. It happened by incredible good fortune that there was a total eclipse of the sun on May 29th, 1919, the first year after the armistice. 2 British expeditions photographed the stars near the sun during the eclipse, and the results confirmed Einstein's prediction. Some astronomers who remained doubtful whether sufficient precautions had been taken to ensure accuracy were convinced when their own observations in a subsequent eclipse gave exactly the same result. Einstein's estimate of the amount of the deflection of light by gravitation is therefore now universally accepted. The third experimental test is on the whole favorable to Einstein, though the quantities concerned are so small that it is only just possible to measure them, and the result is therefore not decisive. But successive investigations have made it more and more probable that the small effect predicted by Einstein really occurs. Before explaining the effect in question, a few preliminary explanations are necessary. The spectrum of an element consists of certain lines of various shades of light, separated by a prism, and emitted by the element when it glows. They are the same to a very close approximation, whether the element is in the earth or the sun or a star. Each line is of some definite shade of color, with some definite wavelength. Longer wavelengths are towards the red end of the spectrum, shorter ones towards the violet end. When the source of light is moving towards you, the apparent wavelengths grow shorter, just as waves at sea come quicker when you are traveling against the wind. When the source of light is moving away from you, the apparent wavelengths grow longer for the same reason. This enables us to know whether the stars are moving towards us or away from us. If they are moving towards us, all the lines in the spectrum of an element are moved a little toward violet. If away from us, toward red. You may notice the analogous effect in sound any day. If you are in a station and an express comes through whistling, the note of the whistle seems much more shrill while the train is approaching you than when it has passed. Probably many people think the note has really changed, but in fact the change in what you hear is only due to the fact that the train was first approaching and then receding. To people in the train, there was no change of note. This is not the effect with which Einstein is concerned. The distance of the sun from the earth does not change much. For our present purposes, we may regard it as constant. Einstein deduces from his law of gravitation that any periodic process which takes place in an atom in the sun, whose gravitation is very intense, must, as measured by our clocks, take place at a slightly slower rate than it would in a similar atom on the earth. The interval involved will be the same in the sun and on the earth, but the same interval in different regions does not correspond to exactly the same time. This is due to the hilly character of space-time which constitutes gravitation. Consequently, any given line in the spectrum ought, when the light comes from the sun, to seem to us a little nearer the red end of the spectrum than if the light came from a source on the earth. The effect to be expected is very small, so small that there is still some slight uncertainty as to whether it exists or not. But it now seems highly probable that it exists. No other measurable differences between the consequences of Einstein's law and those of Newton's have hitherto been discovered, but the above experimental tests are quite sufficient to convince astronomers that where Newton and Einstein differ as to the motions of the heavenly bodies, it is Einstein's law that gives the right results. Even if the empirical grounds in favor of Einstein stood alone, they would be conclusive. Whether his law represents the exact truth or not, it is certainly more nearly exact than Newton's, though the inaccuracies in Newton's were all exceedingly minute. But the considerations which originally led Einstein to his law were not of this detailed kind. Even the consequence about the perihelion of Mercury, which could be verified at once from previous observations, could only be deduced after the theory was complete, and could not form any part of the original grounds for inventing such a theory. I do not mean that they were not based upon observed facts, and I do not mean that they were a priori fantasies such as philosophers indulged in formerly. What I mean is that they were derived from certain general characteristics of physical experience, which showed that Newton must be wrong, and that something like Einstein's law must be substituted. The arguments in favor of the relativity of motion are, as we saw in earlier chapters, quite conclusive. In daily life, when we say that something moves, we mean that it moves relatively to the Earth. In dealing with the motions of the planets, we consider them as moving relatively to the Sun or to the center of mass of the solar system. When we say that the solar system itself is moving, we mean that it is moving relatively to the stars. There is no physical occurrence which can be called absolute motion. Consequently, the laws of physics must be concerned with relative motions, since these are the only kind that occur. We now take the relativity of motion in conjunction with the experimental fact that the velocity of light is the same relatively to one body as relatively to another, however the two may be moving. This leads us to the relativity of distances and times. This, in turn, shows that there is no objective physical fact which can be called the distance between two bodies at a given time. since the time and the distance will both depend on the observer. Therefore, Newton's law of gravitation is logically untenable, since it makes use of distance at a given time. This shows that we cannot rest content with Newton, but it does not show what we are to put in its place. Here several considerations enter in. We have in the first place what is called the equality of gravitational and inertial mass. What this means is as follows. When you apply a given force to a heavy body, you do not give it as much acceleration as you would to a light body. What is called the inertial mass of a body is measured by the amount of force required to produce a given acceleration. At a given point of the Earth's surface, the mass is proportional to the weight. What is measured by scales is rather the mass than the weight. The weight is defined as the force with which the Earth attracts the body. Now, this force is greater at the poles than at the equator, because at the equator the rotation of the Earth produces a centrifugal force which partially counteracts gravitation. The force of the Earth's attraction is also greater on the surface of the Earth than it is at a great height or at the bottom of a very deep mine. None of these variations are shown by scales because they affect the weights used just as much as the body weighed. But they are shown if we use a spring balance. The mass does not vary in the course of these changes of weight. The gravitational mass is differently defined. It is capable of two meanings. We may mean 1. The way a body responds in a situation where gravitation has a known intensity. For example, on the surface of the Earth or on the surface of the Sun. Or 2. The intensity of the gravitational force produced by the body. As, for example, the Sun produces stronger gravitational forces than the Earth does. Newton says that the force of gravitation between two bodies is proportional to the product of their masses. Now let us consider the attraction of different bodies to one and the same body, say the Sun. Then different bodies are attracted by forces which are proportional to their masses, and which, therefore, produce exactly the same acceleration in all of them. Thus, if we mean gravitational mass in sense 1, that is to say, the way a body responds to gravitation, we find that the equality of inertial and gravitational mass, which sounds formidable, reduces to this, that in a given gravitational situation, all bodies behave exactly alike. As regards the surface of the Earth, this was one of the first discoveries of Galileo. Aristotle thought that heavy bodies fall faster than light ones. Galileo showed that this is not the case when the resistance of the air is eliminated. In a vacuum, a feather falls as fast as a lump of lead. As regards the planets, it was Newton who established the corresponding facts. At a given distance from the Sun, a comet which has a very small mass experiences exactly the same acceleration towards the Sun as a planet experiences at the same distance. Thus, the way in which gravitation affects a body depends only upon where the body is, and in no degree upon the nature of the body. This suggests that the gravitational effect is a characteristic of the locality, which is what Einstein makes it. As for the gravitational mass in sense 2, i.e., the intensity of the force produced by a body, this is no longer exactly proportional to its inertial mass. The question involves some rather complicated mathematics, and I shall not go into it. We have another indication as to what sort of thing the law of gravitation must be, if it is to be a characteristic of a neighborhood, as we have seen reason to suppose that it is. It must be expressed in some law which is unchanged when we adopt a different kind of coordinates. We saw that we must not, to begin with, regard our coordinates as having any physical significance. They are merely systematic ways of naming different parts of space-time. Being conventional, they cannot enter into physical laws. That means to say that if we have expressed a law correctly in terms of one set of coordinates, it must be expressed by the same formula in terms of another set of coordinates. Or, more exactly, it must be possible to find a formula which expresses the law, and which is unchanged however we change the coordinates. It is the business of the theory of tensors to deal with such formulae. And the theory of tensors shows that there is one formula which obviously suggests itself as being possibly the law of gravitation. When this possibility is examined, it is found to give the right results. It is here that the empirical confirmations come in. But if Einstein's law had not been found to agree with experience, we could not have gone back to Newton's law. We should have been compelled by logic to seek some law expressed in terms of tensors, and therefore independent of our choice of coordinates. It is impossible without mathematics to explain the theory of tensors. The non-mathematician must be content to know that it is the technical method by which we eliminate the conventional element from our measurements and laws, and thus arrive at physical laws which are independent of the observer's point of view. Of this method, Einstein's law of gravitation is the most splendid example. And with the conclusion of Chapter 9, and quite a lot to ponder, I think we'll end this evening's reading from the ABC of Relativity by Bertrand Russell. Just as in the other readings, there are a few things in there that I definitely understand, and a few that just flew right by me, but I'll consider those later. I hope you enjoyed that. If you'd like to read this work for yourself, as always, you'll find a link to a free ebook from Project Gutenberg in the show description. If you'd like to connect, suggest a boring book you'd like to hear read, or request more from one we've already started, you can drop me an email via our website, www.boringbookspod.com. It's always a pleasure to hear from you. Thank you so much for joining me for this evening's reading. Until our next boring book, good night.